All right. Well, I'll start. I'm Isabella. I'm a PhD student. I also am a founder, and I created Laser Neuron to do something originally in computing, but I switched to actually the missing link between VCs and scientists. So I really enjoyed speaking with VC, and I learned a lot. So switching the brain from science to what venture capital is actually thinking was a very interesting experience. So I want to continue that. That's why we're here. And the Quantum Café was an inspiration for my dear friend Imi, who's also presenting. We used to do this online on Zoom for a few times, and it was also always a pleasure. So I love learning about quantum, and so I hope you enjoy the rest of the event. So thank you. So I briefly already explained that that's what our goal is at the Laser Neuron, is to connect VCs with scientists. We found that this link was missing, or a lot of the times it was the founders that had the idea that we're talking to VC, but it wasn't so much that the scientists were really tapping into that. And I think there's so much potential and learning that we can do from speaking with each other directly. So this is the brief agenda: arrival, having first talk by Kevin, second by Ingmari, having a small break, and then Dr. Jana Lehr's talk, and later on the panel. So this is our second event. Our first event was in Cambridge at Ethos and across the street from MIT. And we had really nice people coming in. We did our Quantum conference, and we really got the ball rolling for people that didn't understand anything about quantum and people who did, and it was an open dialogue, and it was really interesting. So today we have these are speakers, and let's go ahead and get started with Dr. Kevin's talk.
Okay. Thank you very much for coming today. It's really a pleasure. It's my first Quantum Unconference and the first meetup that I will talk about quantum computing. So, I mean, personally speaking, today I'm not going to talk about any NVIDIA stuff. So, because, well, I can't. But I really want to share my passion with you guys about what I have learned in the past 10 years of working in quantum computing. And yeah, I want to give you like a really tiny gut feeling of how complicated is quantum computing and what are the layers that you need to kind of know about. So what is this talk about? It's about taming the qubit. So the qubit is the basic unit of information of the quantum computer. And these are a little bit temperamental units of information because they like to change their behavior during the computations. And we also have to change our strategy when we are trying to control them and actually communicate with them. So this is basics about quantum computer calibration. And the taming actually turns into tuning. Okay, so it's really about tuning our quantum computer. Briefly about me, during the day, I try to do some quantum science. So it's been 10 years that I'm doing quantum computing. And during the night, I'm a rock star. And if you want to talk about music, just come and talk to me. Yeah. So what is a quantum computer? So there are several types of quantum computers. There is not one answer. So on the left, we have a superconducting qubit-based quantum computer, which can be, for example, Google, IBM, IQM. There are several players. And on the right hand side, there is a trap-dion quantum computer. I think the photo is a bit misleading, but I did my PhD on this device here. Which is a trap-dion system from the University of Innsbruck. And in this calcium-based quantum computer, we try to do a custom accelerator for particle physics simulations. So we co-designed the software stack and the device to really have the one-to-one matching of these theories on the quantum computer and cut off all the overhead that our general system would have. But yeah, so these are very different systems. Okay, one is super cold and the other one is low and room temperature. But what is really the common thread is really our qubit. So how information works. Usually in a classical computer, you have the bit, which is just like a switch that can be observed exclusively in 0 or 1. While the qubit, our very temperamental unit of information, actually has a new property. So, I mean, there is 0 and 1 again, but this can be in a superposition. So it can be 0 and 1 at the same time with some probability. And also we can have entanglement, and entanglement is a very particular form of superposition in multi-qubit systems. Okay, I cannot dig into this, otherwise we spend hours. But yeah, if you really want to visualize it, if you're very technical and you want to go home saying, yeah, I looked at equations, this is something like a vector of a unitary length on the sphere, or on what is called the block sphere. And the equation of the state of the qubit is represented by this linear combination. But forget about it, this is not important, okay? Okay, so if we know that the qubit is temperamental, okay, then what are quantum computers? It's like a very evil sitar, okay? Our quantum computer basically is made by many qubits, which are our strings, and we can tune our quantum computer and the qubits actually, by using these knobs. I hope you guys have ever played like an instrument like a guitar. How many of you has ever seen a guitar in your life? But yeah, yeah, thank God, you never know. Yeah, and then you can pluck the string and you produce a note. And then if you want to represent your melodies, you use a diagram. Like here, you have single notes or you have chords, and you can play multiple notes at the same time. So what happens on the quantum computer? You have a quantum circuit. It's kind of resembling the same diagram. You have the lines, which are your qubits, okay? And then you have the gates or the operations, which is like playing a note on your in the melody, and you have single qubit operations, you have the chords, the 2-qubit operations, and you have the measurements. Okay, so what happens in reality is that you start reading from left to right your quantum circuit. You have the single qubit operations and the 2-qubit operations and the measurements, and you build your algorithms. But in reality, it's not so ideal. Nothing is really ideal. So what you have is that you have some errors associated with your operations. Each operation has a tiny error that is inherent to the system, to the environment, so many different factors. And what we do is that we need to calibrate or tune our quantum computer so that the noise is really reduced to zero for this operation. So we can tune the operations, but unfortunately, Mother Nature said, not so quick. So actually, there are these parameters called T1 and T2 times. And these basically are the times under which our qubits actually die naturally. Okay, so the information cannot stay there forever. After a little bit, this dissipates into thin air and you lose your computation. So you want it's like on the guitar. Some notes have to be longer, some notes have to be shorter, and you want your melody to sound amazing. So you have to know how long you can sustain a note, for example, on your guitar. But whatever. So, okay. So we have these errors. So what can we do about this, So we can calibrate. Is the calibration boring and annoying?
Yes.
No, it's not. So calibration is repetitive. It's something that we have to do very often. And it's very beautiful because we can automate it. So once you know what you need to do, you can do it automatically and improve it over time. So it's made by 2 parts: system identification. So first of all, you need to know what you're dealing with, how your quantum computer looks like, what are the pros and cons, and so many parts and whatsoever. And then there is the control optimization. So once you know what you're trying to control, you need to be able to control it perfectly with really high precision. So yeah, see it and then you kind of. All right, so basically, yeah, what is happening, you identify your knobs, okay, in your system, you're tuning some knobs like in the radio, and then you use the device somehow, you see what the device gives you back. So you need to make some readouts, and then you make some decisions. If you like the answer, you tune you don't tune your knobs anymore, and if you don't like it, you continue, playing with the knobs. But yeah, and this is like in the concert. So you play a few songs and then your strings play tune. So you turn the knob, you pluck the string, and the tuner tells you, hey, go higher or go lower. And you repeat this process for all the strings after, a few songs. Okay. But how do you monitor this behavior over time? What is this tuning really about? So you have a simple experiment. Maybe you have a bit in 0, you apply a bit flip, and what do you expect? 1, right? But what if your bit flip has some noise? Maybe sometimes you get actually still 0. So you are like, oh, damn, like, I think we did something wrong here. So what you do is that you repeat this over time a lot. You use some cool mathematics. And then you can plot over time through the calibration runs what kind of parameters work for you. And you plot it over time, and you see that some parameters are really anomalous. So you should be like, oh yeah, I will never use this. And then you roll back to your calibration parameters. So it's really an exploration over time, use a lot of statistics, okay? But yeah, why is it beautiful again? Because it's just a loop. So you choose an experiment that you know what you need to expect, kind of. You configure the hardware, you execute a pulse sequence. This is a secret, what is a pulse? So you apply the measurement, you analyze the data, so you try to understand if the knobs that you turned did a good job or not. And then you update the parameters and you validate and iterate. And you do this the whole time, okay? All right, so I mean, we have an idea what is the calibration loop. Any questions so far? Yes.
Yeah, just I want to try to formulate this well. So like this is a basic primitive. We have bit flip X, we have the prepared zeros, so then we have a measurement.
Yeah.
I see how it's smart to start with something so simple, of course, but I'm just wondering how that scales when you have more complex operations, like when you start to have entangled pairs, or you have like a Hadamard gate or whatever other operations you might be doing. Like, do the nonlinearities, can they defeat the calibration in some way? And if they do, how do you deal with that? Just kind of
you build more interesting experiments. And yeah,
just keep building Lego blocks. You say, okay, now our bit flip is safe. We know our prepared state is really a 0. Because if this is consistently showing 1, you could be pretty sure.
I will show you something.
Okay, we're going to keep going.
Okay.
Good.
Yeah. Yeah. So I said, okay, there was a secret sauce in our loop, which was the execution of pulses. Okay, so then what are these pulses? The secret. Gates, the operations are pulses, okay? So in your quantum circuit, the reality is that these tiny blocks and drawings are just signals, okay? We try to launch some signals towards the qubit, and this is how we control. It's like controlling magically at distance the qubit with your hands, okay? You just throw a signal. So yeah, how do you build these signals then? You know, what are the knobs of a signal? What is really a signal about? Well, we have several signals. We like some of them more, some of them less. And for example, we like a lot the red Power Ranger, which is the Gaussian pulse. And we like some of them a little bit less. And we really don't like the square pulse, which is the blue Power Ranger, because yeah, this is really not allowing us to control precisely, as we said in the beginning. But this is also still a guy that we need in the team, like the Power Rangers, you know? So, okay. Then also what we can do is that we can mix them, we can fuse them with some nice choreography, and then you get a new efficient pulse operation that is all combined, much more efficient and precise in controlling the qubit. Yeah.
What properties of the square pulse are like not things that we want versus like.
So the difference is, for example, as you can see, this is really nice and smooth, right?
Yeah.
And this is a square edge. So if you make the Fourier transform of this has a lot of frequencies in it. And so basically, it's like shooting with a bazooka to a little apple. And this is like using a tiny pen on the apple, you know? Okay. So yeah, I mean, we said we have the pulses. What are the knobs? Yeah, go ahead.
So you first design one test like the bit flip, and then you go ahead when that works. And
sorry, go ahead.
You first design one like bit flip, and then you tune the parameters, and then everything works out fine, and then you move on to another test. Then you restart basically and tuning some parameters.
Yeah.
But then you always need to ensure that the tuning you're doing for parameters, the bit flip still works, right? So if you tune and then currently you tune something and then what you're trying to test second was it's now working, but the bit flip is not working anymore, then that is useful. Right?
But you don't tune single operations. You tune properties.
Okay.
So if you need to tune your pulses, okay, so basically tuning your pulses, you can, so the X gate, for example, the bit flip is just a pulse. We don't care about it, you know? It's like pressing all of these keys on the synthesizer, okay? You don't tune each single note and just make sure that overall, you're able to generate all types of sounds, okay? And then you can make any type of operation, okay? So it's a little bit, I mean, a bit more fundamental than just making the bit flip. So anyways, I hope if you have questions after the talk, then please come to me and I will give you a full lecture, okay? But yeah, so I mean, what you can do is that you have the pulses and you can design your pulses, like for example, in some production digital tool or on an analog synthesizer where you're like really tuning a lot of knobs, okay? And then playing your melodies again, it's like the quantum computation. So what are the things that you really need to study about a pulse is the frequency, so you have a faster rate or a lower rate, the amplitude, so you make your signal wider or smaller, the phase, so you can shift it in time, okay? So maybe if you have the sine, it doesn't start from the origin, but it starts a little bit shifted. You have the duration. So, I mean, we have the beep and we have like beep, so we have different durations, and then we have the shapes that we saw before. So we can combine them, and after combining them, we can understand the rest of the properties. So, okay, question, how do we tune these things? We do the experiments, okay? So it's a little bit more fundamental now than the bit flip, because I didn't want to bomb you already with the abstractions. So first of all, you can do, for example, spectroscopy. So you need to find the right frequency to communicate with your qubit, okay? So your qubit needs to know, hey, this guy is talking to me, and I need to change my behavior, okay? So what happens is that it's like singing towards a glass of wine. You change your note and you go to the right frequency and the glass of wine starts vibrating. When this glass of wine starts vibrating, it means that now maybe you have established some form of communication, okay? Similarly, this happens with the qubit. So you create a signal and you try to find out what is the right frequency in which your qubit resonates. And then basically you can manipulate the signal based on that frequency so that you can make, for example, the bit flip. Okay. Then another experiment you can do is called the Rabi experiment. This is about the duration or the strength of a signal, for example, of your operation. Imagine that you're pushing your best friend on the swing and you do it rhythmically, okay? You continue, but every time that you touch the kid, okay, or touch your friend, you push your friend with a little bit longer push, okay? In the beginning, you just touch it, you touch his back, and it's not moving. And then you touch it for longer, and then you touch it for longer, and you touch it for longer, and you see that now the swing is starting to move, okay? So this is really about understanding for how long to push the swing, so that also like the swing doesn't come back to you and bumps into you, okay? It's about finding the sweet spot. And then, I mean, this is two examples of experiments that you can do for understanding the properties of an operation, our signal. But also we need to understand the qubit stability, those things that we cannot actually tune, but we need to keep into account. So this T1, T2 times, the natural die out of the qubit. And you need to know it because, this is really still fundamental, although you cannot tune it. And this is like understanding after how much time two metronomes can diverge. So the Ramsey experiment, there is Ramsey. And what happens is that Ramsey is starting two metronomes at the same time. And these two metronomes, basically, they are clicking, making a sound at the end of each period. So at the beginning, they are synchronized and doing ta, 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 ta. But then, after, the first kick in image 2, Ramsey is waiting. And in image 5, the two metronomes, because they have a really tiny divergence in the period of their oscillation, they start to doing, instead of ta, 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 they do ta, 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 ta. So you kind of notice that these are not synchronized anymore, okay? And this is kind of trying to be metaphorical, but in order to make you understand the stability of the qubit. But if you repeat this experiment from 1 to 5, and you measure in how much time it takes for these two metronomes to diverge, basically you can understand, it's like understanding the qubit decay time, okay? And because qubits, I mean, they have phases, And basically, the when two metronomes shift apart is like the drift of a phase, basically. I hope that you guys are going home with something about the Ramsey experiment.
Why is it a shaft that is doing the metronomes?
It's supposed to be Gordon Ramsay. Yeah. Okay. So what happens is that, okay, if I have 1 qubit, sure, I can make all these nice experiments, but what about if I need to tune 1 million qubits? How long is it gonna take? Well, I mean, for this you need automation, as we said before, and well, we have a whole graph, directed acyclic graph, dependencies between experiments. So you start with your frequency, so you need to find the communication channel with your qubit, and then you do pulse duration, the T2 time, the T1 time, and then there is like, this is really tiny, so there is a whole zoo of experiments that you can make. And then as you go with the computation, you figure out, hey, this guy is not working anymore, so you invalidate the full graph. But if this guy is not working anymore, you just invalidate these, and then you rerun these experiments, okay? So there is kind of some dependencies, and if some things are not working along the way, then you can understand, you can spot actually what went wrong in your system, and then you can rerun some experiments. And if you need to scale, algorithms, more experiments, what do you think? Any idea?
More Gordon Ramsay.
We have calibration pipelines, more software, more. So yeah, you have the scheduling of orchestration, you have estimation fitting, user jobs, dashboards, logging, monitors, all kinds of things. And this needs to connect them to your experiment, to your device. So this is the quantum hardware with control electronics and experiment executor, for example. But then what does it mean in this image? That, yeah, sure, we have a lot of software and nice mathematics going on, but then it means that also hardware matters. Because at the bottom here, you have your quantum processor, but the quantum processor really is just one tiny element of a really big stack of different technologies. Okay, imagine you have your superconducting qubits, one from IBM, for example. Don't look at the numbers. These are just indicative of the orders of magnitude. You know, it really depends on whoever builds the system. But you have, for example, the quantum processor, you have the dilution refrigerators, microwave electronics, you have the FPGA and all this control electronics. And then on top of that, you have the CPU and GPU that is our executor that launches the experiments along the step. Okay. So all of this needs to happen really quickly, especially for superconducting qubits. So we have a 1 to 3 microsecond round trip. So the full thing going on, you know, up and down from the FPGA to the quantum processor. And yeah, well, the signal has to be also good. So if any of the elements in the chain is actually not performing well, then we have to throw away the whole thing. No, I'm joking. But at least you should substitute, and you should be aware that if some parts are faulty, I mean, the quality of the result is actually bad. Okay. So calibration is a full stack engineering problem. And what could we add on top of this? Of course, AI. So yeah, in the future, we could add AI within our stack and actually make this whole process self-tuning, completely automated, even beyond our software infrastructure, for example. And the AI could take care of this on top of our chain and in order to reduce latency, for example. Yeah, these are an example, but who knows? Someone has to come up with something. So yeah, quantum computer calibration in short. So what we have seen today, I hope you guys are going home with something about quantum computer calibration. You tell your friends that you understood. But yeah, what did we really see? What is a qubit? Okay, I hope you understand what is a qubit now. You can say, yeah, it's a vector on a sphere. You know, it can be like when you're having the happy hour. So how programs actually are not ideal. So our ideal program in reality has always some error associated to the operations, and we have also this decay time, the T1 and T2 times. then yeah, that calibration is really nice to automate, and it's just a nice loop where you have to pick and choose the different parts of the loop. And well, you have your pulse shapes that you can mix and that you have to tune in order to implement these nice operations. That software really matters for scaling, and also hardware really matters. That's it. Thank you very much. Any questions?
Oh.
Go ahead.
No question. Part of my ignorance, but calibration is task specific, or like you calibrate for a specific task.
No, you calibrate for the full spectrum of operations. So you choose. So it's also very theoretical. So there is a third dimension. So software matters, hardware matters, mathematics matters. Okay. So you need an application, and then maybe you understand what your quantum processor does. So you try to match your experimental pulses possible on the device with the mathematics of your application. And then you figure out, hey, yeah, actually I need H, the bit flip, and the CMOS, okay? And then once you choose your gate set, it's like choosing your assembly, okay? Then basically you develop your whole infrastructure to be able to support this assembly. So of course, you cannot optimize for each single tiny iteration. You try to optimize your system and the calibration for the full spectrum of the assembly operations of your system. And then, of course, if there is something really particular, then you make some extra experiment to really fine-tune that operation.
What's the most challenging aspect of the calibration framework?
It's a lot of things. It's a lot. As I look at this image. It's a lot of things. So I have to say that probably if you ask me from the top of my head, is the mathematics behind it. So not only the quantum information part, but for example, estimating the quality of your parameters. So you don't want to, if you have 1 million parameters, let's assume, okay? You don't want to test each one of these. You kind of need to have a gut feeling, okay? And there is some nice mathematics about it, maybe statistics, based on statistics. And then you try to figure out, based on the device physics, for example, what kind of knobs actually should I turn immediately and in which position to put them. Also, the control electronics is tough. Yeah, so the hardware matters really. Yeah.
So feel free to ask Kevin questions in the coffee break.
Just one question out of curiosity. How often do you need to calibrate? Because we said that the drift happens also over time. So I assume the system is working, it starts drifting.
Yeah.
Is it like a continuous monitoring system that you have to always calibrate, or like you said, like, let's say every 10 minutes I need to calibrate?
Yeah, you can. So the thing is, it really depends on your application and what you're trying to achieve. So nowadays we are getting into the fault-tolerant era of quantum computers. So far we were doing NISQ, which was what is called a near-term, intermediate quantum devices or whatever. I'm sorry. But yeah, this is when we were using our small chips with 20 qubits or 30 qubits maximum, and then we would try to run algorithms on that or quantum machine learning. I heard some of you guys do on top of this. But this is not enough anymore. So we really want them to be really resilient. So we use actually error correction, which is basically something like you do in classical transmission. So you send like your WhatsApp message and it's sending the bits, and there are some bits that are just for redundancy to understand if something got broken over time. And well, it depends now. So if you want to do error correction, then what is the good rule of thumb for testing out what's the health state of the quantum computer? This is ongoing science. There is a lot of state of the art, but we can talk about it later. Yeah.
Thank you so much.
Thank you.
Now we have Ingmari's talk.
Yeah, thanks Isabella for organizing this whole event, and thanks for coming here so we can talk and exchange knowledge and so on. I'm giving a talk which is a bit more general, and there will be not a quantum computation expert at all, but I come from quantum sensing more. And that's what my talk's going to be about, but from a broader perspective, because I thought I was talking to VCs more, but I see there's a lot of scientists here as well. I did my PhD in non-neutral plasma physics at CERN in the antimatter factory. And yeah, this was more penning Monbach traps, like tracking antihydrogen, pulling it down with electrons, and then doing some fundamental research with it. But then afterwards, I went into the block business. And yeah, this is like one part of the experiment I used to work on until recently. So you see like the strontium beam here. So you actually see the fluorescence from the atoms. And yeah, so an optical atomic clock is also a quantum sensor. Some are better than others, and they have different kinds of properties and so on, but you can use a clock as a quantum sensor. So if you look at can you see this? This is like big enough. Yeah. Okay, if you look at it from a bird's perspective, let's say, then you have quantum sensing, quantum computing, and the quantum sensing. I mean, we have had sensors around for a long time. Chronometers, so clocks, have revolutionized our world before, so it wouldn't be the first time with other sensors. I'm going to talk about this in a little bit. But in the quantum world, I mean, we exploit what the first speaker, Kevin, said already, that we have quantum superposition, entanglement, and so on. So, I mean, these are great properties to exploit because, yeah, they give us some level of sensitivity in the quantum sensing world. And in the computational world, you have the property that, for instance, you can solve the traveling salesman problem at the same time. So you reduce the computational time massively. In terms of business, I think that quantum sensing is a little bit further in terms of the commercialization than quantum computation. So you have quantum sensors. I think one part of it is because quantum sensors are more distinct, so they are more to like one specific object, let's say, like clocks. You want to have a clock, and then you can measure like different things with it, among them time. And for the quantum computing, so I think the NIST means noise intermediate scale quantum, but I wrote it down because I thought I would forget it, what it means. So maybe you can tell me later on like in which stage we're entering into now. I think in general, this is still correct that the quantum sensing is a little bit ahead of the quantum computing in terms of commercialization. And then applications, yeah, and we have navigation, but we also had navigation 200 years ago with a longitude problem. We have gravity mapping, you have precision timing, of course, seismic detection, so very important for earthquakes and so on. So you can use clocks and fibers and so on for that, but also other devices. And then in the medical realm, you have a lot of different detectors that are coming onto the market or have come onto the market. And in quantum computing, I mean, I'm not gonna say much here, but I guess optimization problems, cryptography, drug discovery, if you think about like finding the ground state of a huge molecule, like how do you do that classically versus with a quantum computer, and so on. And then of course there's the AI factor now too, everyone talks about it. Yeah, and then as a trust factor, I mean, here we have quantum sensors, and they're being sold. And also there are quantum computers which are being sold, but they are still in a, yeah, let's say, like it's like a stage where you develop them still further and use them for toy problems. But once they will not be toy problems anymore, then we have the real revolution. Yeah, so hype or revolution, I've heard like a lot of people say, yeah, quantum computation, quantum sensing is a hype or something like that. But what does that even mean? I mean, I don't know if you know this clock here. It's in Greenwich. You know it, yes. there's a wonderful museum. There's not just this one, and this one is actually like from the outside, it's like the most boring one, because the other three Harrison clocks, so Harrison was a Scotsman, and he built these clocks in his lifetime, and there's the operating, and you don't have to put any loop on them because they have a special type of wood that lubricates and still like 200 or more years afterwards. So they're actually doing their movement. And this clock revolutionized navigation because you didn't know where you were on the ocean. So you could, like, by the sun, you could extract, or you could calculate the latitude, but not the longitude. So people were crashing into the coast in Cornwall, for instance, or elsewhere. But then Harrison, over his lifetime, over a long time, built these different clocks which operated with spring systems and not with pendulas. So pendulas don't work on a ship, right? Doesn't really make sense. And he came down to a very elaborate system in his fourth clock. So this is the fourth one, that's why H4, to 1 second a day of deviation. That's it. So that was revolutionary. You could take your home time with you, compare it with the local time that you could determine through the sun, like where the sun was at, and then you would know roughly where you were in your longitude. So you weren't lost anymore. So this was one of the revolutions that happened before. And then also, I mean, good old artificial intelligence. There's different definitions of artificial intelligence, of course. Some are thousands of years old, but the one that is 70 years old from the 1950s, we are living through the revolution right now, right? I mean, it's changing all our lives. So if we start from Harrison's chronometer to the quantum clocks, then we have like deviations that get smaller and smaller per day. So quartz oscillators 10 milliseconds per day, then the cesium beam, 1 microsecond. And then we go to optical beam clocks, 10 to the power of -15 per day. And then we go to optical lattice clocks, which operated typically like 10 to the power of -18. So we have a 1 with 18 zeros behind in difference. So basically, we don't have a second coming up anytime soon. But there's also something else. I mean, there's other things. I mean, the clocks on satellites, very important for us, right? For every one of us, every day when we find our way here for the GNSS, or the GPS, as it's usually known. And then frequency cones. So a frequency cone is a laser, which is like a rainbow, literally. So you have equidistant parts of that laser, and you span a whole octave. And if it's in the optical regime, then you have a rainbow if you split it up, or it's paused in the time domain. And with this one, you can convert from an optical clock that is frequency stabilized. I'm not going to talk about what that actually means, but you can ask me later. You can convert that to something which is countable by electronics. So this one, we needed it. I mean, there were some like huge buildings like this one for like one down conversion from an optical frequency down to an electronic frequency. But with this one, you have it like in a box. And I think the smallest ones are about this size now. Yeah, evolution of computation. This is where I don't know so much about. So I'm just going to say there was, for instance, Babbage and Ada Lovelace, and they did an awful lot, but it was all on paper. And then fast forward, okay, I mean, we have Turing machine, etc. But I mean, we're here right now and there, right? So what's going to come of that? Where's the revolution actually going to start? I don't know yet, but I guess we will know in a few years' time a little bit more, and then once it hits us, then we won't know anything anymore because there's so much at the same time. Okay, so what's necessary for all that in the quantum technology? I think we don't need so much invention, we rather need innovation, because there's lots of information, lots of papers, old papers, which are in the drawers, which we just need to pull out and understand properly, and then turn into products. And for this, we need technical and technological skills, of course, but we also need business knowledge, and we need translator roles, because if you don't have that translation, then how can you communicate about the whole thing? And essentially, I think you need great people with different overlapping expertise who work together. And I didn't really know like how to put that into words, but I recently saw a wonderful talk by Franziska Greinert at the LEAP in Adlershof. And she was so kind as to give me some of her slides, which I won't explain in detail, but yeah, but you need to kind of have different type of people. So you have like the quantum concepts, and some people are very good in that and they have a PhD in that. So they feel like all these like from B1 to C2, if you think of language skills, maybe that helps. But you also need the business side and you need the technological side as well, right? So how do you map that? How do you get all these people together who together combined as a team can do a good business, like a good startup or whatever it will be. And yeah, here she has like a slide on like different types of people. For instance, a quantum technology practitioner maybe doesn't have so much knowledge yet, but practices it over a website, uses some computational services from a quantum computer, so or a quantum technology literate person. So some people maybe who come here, they're not literate yet, but they will be soon, or they are already. And then of course you can branch out and you can become fully proficient in any type of area. Yeah. Okay, now I know why. Yeah, so to summarize everything, so I think a lot of people agree on that also is that we're moving towards quantum sensing revolution. So it's a revolution in terms of what we can sense. I just gave the example of atomic clocks. I didn't go into the details, but literally you can, with the best clocks, you can see like a shift of 1 centimeter difference in the gravitation above Earth, for instance. I mean, this is crazy. It's like 1 centimeter, you know, if the atoms which are measuring or which you measure for the clock are here or a little bit higher. So you see that in the signal. You see everything which is evolving. You see the Earth coming up and down. I mean, you think of the tides in terms of water. There's also tides in terms of the soil, the Earth. Right now, we don't feel it, but the clocks feel it. Also in quantum computing, I think it's going to come a little bit later, but maybe I'm wrong. Yeah, so we do not know exactly when it will hit, just like with AI. It took 70 years and now it's here. Yeah, and then the growing quantum technology ecosystem needs a set of great minds and people with a diverse set of skills. Translation and literacy of quantum technologies is necessary. So I think this is necessary for everyone. It's just like reading and writing, right? It's like not everyone could read and write. And now we need to learn to read and write in a different type of language. And yeah, for me personally, I'm looking forward and also for a way to contribute. So I'm open to discussing. Like I have no idea where this whole thing is going. And yeah, I'm very happy for the opportunity of speaking with you. And that's it. So thanks for the motivation.
Oh, any questions?
So with the clock, it was very clear why you needed the clock to measure the longitude. For this kind of revolution, what can I expect from it?
From the clock?
No, the clock was good for navigation, but
yeah. Yeah, okay, what you can, yeah. I mean, one example that people talk about a lot now is GNSS free navigation. So GPS, you know what GPS is, and GNSS is the actual term for it. So GPS is the American part of the GNSS overall system. Let's put it like this. And you need it to navigate, right? Now, like most people use it. So if you are on a ship or so, you need like a unit that navigates even if the GPS is jammed, because yeah, you can jam GPS pretty easily. You can just like get the signal from the huge Störsignal, like some noise, a noisy signal to overlap it, and then you can't use it anymore. So you need something that you have in the ship or in the self-driving car, which always knows where the car is.
Without satellite.
Without a satellite. This is one application. It's not just clocks, like there's other like types of then geodesy. I mean the Earth is not flat, right? But the Earth is also not a sphere. It's like an egg. A little bit.
Oblate.
Sorry?
Oblate sphere.
Thank you, but it's not even that. I mean, if you look closely, then you have deviations that in terms of what kind of material you have underneath. So you can use gravimeters for it, like quantum ones, that can test that. And also the gravitation would change, right? So you can use clocks again, like the really good clocks, to see what they feel there. You can literally see the Earth moving underneath you with these devices. So there's a lot of applications there, and I mean also in medical imaging, like when you're able to pick up the slight magnetic field that our brains produce, and you can pick it up with a quantum sensor, and you can turn that into information that's like the medical diagnostics, and that's great, right? So like all these kind of things. So think of anything that produces a signal, and you can pick it up. And then you have a quantum sensor, if you can make it first.
Thank you. So it's really fantastic. But now I have the question, what are the limitations of this technology in space, for example?
In space?
Yeah.
So what do you mean exactly with limitations? Because I mean, I can give you one limitation directly. So for instance, it's if you put a clock in space, then you need to transmit the signal somehow. And if you don't have a fiber, right? Like an optical fiber from the satellite to here, because it doesn't work. So you have the free space transmission.
Yeah.
There's a lot of errors in there because you have atmosphere between. So you need to kind of find a way to cancel that out. But then you also have a fundamental limit, because if you send a signal, it will travel a while.
Mm-hmm.
You can only correct so and so much. And this depends on the travel time. So the longer it travels, you kind of average over some noise and you can't get it out.
But if let's assume that in 30 years we can solve these problems and cosmic rays don't hit the whatever.
No cosmic rays.
Maybe we feel it is some magic. Okay. What do you think would be an interesting application for this technology in space for them? Or you don't see any path forward?
For atomic clocks, for
Yeah.
instance?
Yeah.
I mean, that's maybe not everyone's type of interest, but I mean, I would be interested if they finally see dark matter. That's one thing, but that's maybe not an application, so to speak. Yeah, I wonder what do you pick up with it, maybe from like further away even. I mean, you can like, of course, like focus on Earth, but maybe it's already good if you have like a network of clocks, and this is being built, right? I mean, you have European fiber networks that are growing. So you connect like different clocks. But if you put them also in space, I mean, for fundamental research, it's definitely things like dark matter. Also,
Fundamental research. So.
but that's not an application per se. Was it for you?
Yeah, I would call it also an application.
I mean, then you can like distinguish between like different types of models for dark matter. So there's some chameleon type dark matter models where the matter of the Earth, the mass of the Earth, it kind of shields the fields of the dark matter. Then you would see it on the satellite, especially if you're like higher up. I mean, there are different orbitals, right? Yeah.
Interesting.
Yeah, but I guess also you could pick something up from further out.
So it's astrophysics, basically.
Yeah, I mean, I haven't really thought about it in that way, but I guess.
Can I ask?
Yeah.
Actually, these days, when you want to train large models, you need very precise time controls. So they're actually using very precise atomic clocks or quantum clocks. There are actually 3 companies which raised just now in the US, just to make sure that your models are trained so that they don't, if they wait, the time is offset, and you lose actually the training, like the weights don't transfer properly and all. So they are actually to make sure that precise timing. They're actually using these precise quantum clocks. I think inflection.
In data centers also?
Yeah, training large models.
Faster clocks, yes.
Yeah, they are actually looking for as precise clocks as possible. No. So even as quantum clock.
Yeah, I mean this is a very straightforward thing that you have the ticker, let's say, in which you can do parallel programming. Yeah.
How do the sensors connect with traditional hardware?
Well,
Is it
for
USB cable or like what is this interface that you're using to?
well, I guess that depends on the quantum sensor, but I mean for the clock that I was working on, basically the pendulum is the laser, and you stabilize the laser, so you make it really, really small, and you stabilize the laser to a certain transition. And we also use this like block sphere that you showed before, this like sphere where there's this like one vector, not just the qubits. Like the qubits don't have the only, they're not the only ones you need it. And you can like manipulate it in like a specific way, Ramsey spectroscopy, and then you can make like a really fine feature. So you stabilize your laser to it, and then you read it out with a frequency comb, and you have a number basically of the, so it's so I guess we could use speed, but maybe it's a little slow. So it depends. I don't know. I mean, depends on the quantum sensor and on the application, I guess, and what you want to connect it to as well. But there are endeavors, for instance, at CERN, they have like a quantum project where they try to combine a lot of different quantum sensors to measure dark matter and other things. So, yeah. Any questions? Okay.
Thank you so much. Okay, so how about we take a 10-minute break, some coffee and tea, and then we come back in 10 minutes. Thank you. Okay, so now we're going to join the next session, which is Dr. Jana Lehrer's talk on science to business practice, and following that will be our VC panel. So thank you, Jana.
First of all, thank you, Isabella, for organizing this. I think it's a really nice format. Thank you also for you for coming here. It's great to see that there's so much interest in this topic. When Isabella asked me to give a talk, I first, of course, thought about talking about physics, because I'm a physicist and I love physics. Nevertheless, we are here in this very specific setting. We have then the question round with investors, and we have the science talks. So I thought it's a good idea to talk about bridging this and also joining, not joining, but connecting the science part with then the business and the which also relates to the investment part. So before I dive into the detail, I may also say a few words about myself and why I think this topic is important. So I studied physics and I worked in basic research for several years, really basic research. So particle physics, quantum optics. Quantum optics at that, or the quantum physics at that time was still, well, quantum computing was still a bit science fiction, so the early stage. And I really enjoyed science and research. So nothing else, no business, nothing else. So that was my life. Then I moved on and moved into software engineering. Software engineering, we designed in this company, it was a medium-sized software company, we designed applications for customers that had a real problem. So it was a complete different context than in research. I said, well, this world is also interesting. So that's you can do something and you have impact. Yeah, you see the results you're producing are really used. So I enjoyed this very much. And I continued working in business and had several different opportunities in focus management consulting, business operations. So, okay, that's quite okay, different perspective. But then I realized at that time I worked at IBM. IBM has a quantum computer. And that brought me back to my roots, to quantum physics. And I decided, first I joined the quantum ambassador team, but I then decided okay, I'm going to a startup and help the startup to scale up, a startup in quantum computing, to be really closer again to my passion in physics. In this entire journey, I learned a lot that there are so many different perspectives on how people look at the technology development, and also where they focus. And especially in the startup world, it's super important that you know what all is necessary to build your product, to sell it, and so on. So Isabella talked about that she learned a lot in the conversation with investors. Ingmari mentioned the talk that Franziska has given at this event, so that there are different skills needed to really be successful as a startup or not only as a startup, but really mastering the technology transfer out of the lab into the business. So I think this is, as we have several founders here that coming directly from the research, from university, from research labs, going into in this business environment in the startup. I want to share with you my thoughts and what is necessary, what is important, and why we still have challenges in this technology transfer. So why this technology transfer today is absolutely important, why it matters so much. Now, on one hand, we see a tremendous acceleration of the technology development in the past decade. So quantum computing, AI, robotics, and the combination of everything. So here it's getting a lot faster than in the past. So that is also technology development is not just an academic discipline now today. So it's important to really translate and transfer it into business to get really benefit. And it's so important that it's also has strategic value for entire economies today. That's one thing. So we cannot ignore it, and we need to really support this. There are several initiatives, so it is known, so that it does not happen from alone. And especially here in Germany, we have, for instance, the high-tech agenda now. We have several initiatives. In the past, for quantum computing, Germany was one of the first countries to have really large programs to support the development of quantum technology. And there are follow-up programs, and really the focus on it is understood that the support of the tech development is super important. Also, it is known that startups play a crucial role in this entire tech transfer. And so it is also seen that there are a lot of conditions needs to be improved for startups to grow, to be founded and then to grow. So it's super important in Europe. We are very good in research, but we are not so good in translating it into business to get really economic benefit out of it. Now we have several examples in the past where we are great in the early stage in the development, like in microelectronics. AI looks very similar. We do not want to play the same game with quantum. So it's very important for Europe, for Germany, for this ecosystem to master the transfer from the lab into the real business. So I mean, not to an MVP, but really make it commercially accessible to also the mainstream customer. But that's then the challenging part. It's important for Europe and also for Germany. We need to retain the competitiveness. We need the sovereignty. It's a hot topic, and also we need to be resilient. So there is really a huge impact if we don't really master this technology transfer. So there are a lot of problems that needs to be solved, and a lot is already in discussion, in implementation. But I have here one problem, which I consider, and also based on my experience in my journey, as very important. And I would like to make you aware of this. Yeah? Physicists love to talk about physics and techies in a similar way, but what we focus on is mainly we focus on understand research. So how does it work? Because that is fascinating for us. Huh? What we rarely teach, at least in this tech environment, in the science environment, is how we transfer this. So Ingmari, you mentioned from the talk that we need somehow also to translate it to the other world that is non-techy, that they understand it and we understand their problems. So this is a conflict. There are activities to overcome these discrepancy, but still that's one of the, I consider this as one of the main problems in the tech transfer. So when we look a bit closer, go a bit deeper in the tech transfer, what all plays a role. And there's on one hand the science. I think all of you is kind of familiar with science from an introduction. I think the majority have a scientific background, research also in one of the hot topics, quantum and other fields. So the focus in science is, of course, getting something new, understanding, something novelty into this game. Yeah, you need to validate. Yeah, you cannot just come up with a hypothesis. You need to validate what you have. That requires repetition. It requires careful validation work and testing. So until you really have these new theory, the new experiment running. Yeah, that's one very important criteria among others in the scientific world. And the challenge, well, usually if you work at the early stage, the technology later on is still uncertain. So what will you do? Of course, you write in your paper, this could be an application, but usually that's far out of reach. Technology is not the core topic in the research. When we look at the next player in this technology transfer, that's the industry. And the industry stands for everything that is business. It could be service, could be whatever. No? The industry focus on execution. No? They need to build products. They need to sell the products. So that's their main focus. No? So, in industry also, what matters is speed. Yeah? The market is driving. The faster you can execute, the faster you are on the market, the more benefit, the more market shares you may get. And one really important thing is in business, because of the speed, you usually have to make decisions with high uncertainty. So you do not know everything. You cannot explore everything. Just in totally different to the science, where you have to validate everything. Yeah? So here you also already see there are a lot of differences in this, and this is only just one set of. And the third area in this tech transfer is the ecosystem. I summarized everything else. So it is the government with all the rules, legal in the background. It's a financing that enable the financing of the technology development. So everything I summarized here, and they have also again a different focus. So they look more for the future potential. So what can be made with that in the future? How does it help? They have to balance the risk. Yeah? So they have different opportunities, and they have to somehow judge where do we invest, where put the focus, what is really strategically important for the next years. And they would like to have a proof, but there is not. So there's a lot of guessing in the proofs. So of course you can choose also different other logics, but these are somehow the core players that somehow are always present when you want to move some scientific results, develop a technology into a real business product at the end. And you see with the differences, they all have different interests. Each is absolutely valid and necessary, but as they are so different, it's guaranteed that it creates friction. And in the technology transfer, you master this entire game if you can handle the friction and if you can work such that you have all these somehow brought together into one working system. Just the same as an overview. So the science focus more, is it true? The industry, will it work? And the ecosystem, will it matter? So different purpose, different focus in this tech transfer. And what is here? The tech transfer somehow happens here. But that is just in the middle, just at the intersection of these different areas with the different scopes and with the different systems of thinking, of working, and the tech transfer is just in the middle. That shows you, from that you can just immediately see that tech transfer on one hand is super exciting because you have the science, you have the industry, the application, so creating something meaningful, and you have then long-term the ecosystem. Does it matter? Is it not just for me, nice, but is it really has a value also for the society or for even thinking even bigger the human mankind? So that's the potential of the tech transfer. And working at this intersection, then you have so many different impulses from each of these areas, so that it's super exciting. And I think when you already experience this, that it is something you find not so easy in some other areas. But at the same time, it's challenging because you have to know your science people, they think differently. And this is okay. You have to know, and you have to also address them. If you go to business, if you want to sell this to a customer, that this customer may not be even interested in how your technology works. They want to know, does it solve my problem? And the ecosystem, you have to build the company that enables you to build your product. You have to be in this ecosystem. You can use it, but you have to also play with the rules that are available. So that's are the challenges but also the opportunities in the tech transfer. And startups, I think what you're aiming for, many of you, they are just here in this central place. Okay. Before I come, just a little example. You probably all know. You may all know. I want to say, well, what I observed in different settings is that people come with super great ideas, that they're all brilliant, and that they really have also great visions. And very often it's that the failure at the end, or the challenges come not with the technology, but with the way you try to implement it, to try to sell it to the customer, the understanding you have to, from a first stage, which is usually quite easy if you have a great idea, then growing, scaling up. There are so many problems coming, or so many challenges are coming that that are not related even with the technology itself. Now you have to productize it, you have to test it, you have to make sure that it's stable under conditions that are out of the lab. So there's a totally different space. But this also belongs to the tech transfer. It's not the first part, that's the super exciting part, of course, creating a new product or a new idea. But then if you, the long run, that really determines if the technology transfer is successful. And this is the part where we definitely need to improve here in Europe and Germany, so that all the early stages that definitely grow. So the Startup Verband for last year had tagged about 400, 500 new startups in the tech space founded. So this first stage, that's getting better now. But the long run, this is what we master. And so as you are here, think about also the long run. So it's great to have the starting point, but if you want to get really your startup in an economic relevant area, then think about these long run, get all the skills and people that have these expertise together. Yeah, they are so different, these skills, that no one can have them all in one person. So find the people, think already forward, and bring a team together that makes this happen. That's kind of just while we're here in quantum computing, I brought an example from quantum computing. I by myself work for a company. We built quantum computers based on synthetic diamonds. That's a different technology as IQM did. And currently we have about 5-6 technologies in quantum computing that may have the potential to really be the winner in this game. One company is IQM, that they're already pretty fast, and they, at least at the current stage, are quite good in this game, technology transfer. So 2018, that's not so long ago. They were founded by a group of scientists. They grow, they build the technology, they use the ecosystem. And they are now a fully stacked quantum computer company. They hold a lot of patents, also important in this game. And they built quantum computers, they delivered. Just recently they got the unicorn status. So it looks like that, looking good. Also, quantum computing is still a very immature technology where we don't know where it goes. So it's possible to play this game, to really have the growth, the scale up, such that you are really have impact, not just for one customer, but also for a variety. Now, still to be continued, as you know. We need to prove that quantum computing really has the economic value, but it's just the beginning. So my message to you is really know your role in this tech transfer. Know where is your sweet spot. What do you love to do? Are you more on the science side? Are you more on the business side? That's really core. Find your position, and then find the partners that compensate what you cannot know, the complementary skills, and also identify your sweet spot. I think when you are in love with your technology, then it's easy to ignore the sweet spots. But the transfer works only if you really consider the entire picture and partner with the people who have these complementary skills. Yeah, I close with this sentence. The better we understand these different logics, science, industry, ecosystem, the better we shape the transfer itself. Thank you. Any questions? Tom, yeah. Yep.
Thank you for your talk. I would like to ask from the ecosystem side of things, what are some of like the infrastructure or like policy level developments that really excite you?
At the moment,
Yes.
well, that's much of it what excites me. So, of course, quantum computing. I think that's a super combination of technology, that means hardware, software application, and then the use cases, identifying the use cases for the business. So really bringing the value to the business. So that's challenges everywhere, but it's a combination of so different types of. So this is a very general answer.
So more specifically on like the ecosystem and like policy side of things, is there anything that you think will have like a large impact?
Well, I think the understanding that we in Europe need to be faster, that we need to shift our mind from the research more to the business application. This happened now. I think that's compared to 10, 20 years ago, there's a difference. So there is a lot more effort in this area. Yeah, and of course you cannot change everything by a single day. So, but it moves in the right direction. So, and I think this happens. And what is our role also, at least my intention, bring it everywhere. That it's this mindset, that entrepreneur mindset, getting more natural to people than it was in the past. Yep.
When you try to connect all these ecosystems together, what do you think is the biggest bottleneck in Germany at the moment?
Well, there are many bottlenecks, also known bottlenecks. Now, and depending who you ask, tells you this is important, and this is important. What I think is you cannot remove just one. For instance, that one argument is we don't have huge enough funds from venture capital to really support the big rounds. That's one argument. There may be others, right or wrong. I think in general, the history in Europe is different than in the States. But if this is really the only argument that blocks startups, I don't know. But if you solve this, then you have regulatory questions, in really minor stuff that could kill you. You have and you have this mindset thing that it's in Europe not really this try and fail, try fast, fail fast, or just this is also not. And I think for me this is the biggest blocker. So if you overcome this mindset, then we find solution also for the other one. Yeah.
I have a question that just also lay my thinking, maybe we see it differently. So in this, there is a couple of blocks or circles. And now with the current AI shift that is happening, where now all the researchers, they've already fed to pretty much. We have all the data from research. We also have pretty much consumer data where you can sort of match product or market, what the market is expecting. How do you see like businesses building sort of these modes that can compete with this new technology trend. I don't know, it's very interesting in a way because for startups, there's a lot of momentum, but it's also the barriers are going down quite quickly. How do they compete? How do you see it, like startups competing going forward, like with this sort of shift that is happening?
So one thing that is we should distinguish. No? One is knowledge and information, and the other thing is really execution. From AI, you get a lot of information. Yeah, you can get an information overload, but knowing and then really executing, bringing this to a product that helps the customer, that's a different story. And what we see with what I think AI can help us, but only it will help only if you know what we do and where it is the purpose. And so I probably won't tell you, well, you have to shape your, when if you don't ask it, maybe yes or not, yeah. So, but what is the typical intention for you as in a startup to create your product? Is it just you love the technology? Then you have a problem with or without AI because no one may need it. But if you have the mindset, I want to solve a problem in the business that the real business has, yeah, and this is that, then you have by far more chances to succeed, and AI just helps you to organize it in a better way, for instance.
I'm confused. So I'm someone who's actually worked for deep tech startups off and on as in the go-to-market space for quite a while. And I mean, I do see a lot of products, of course, based, of course, in deep tech and deep science, and there's excitement, but I somehow feel like a lot of products that are based off of PhD's research or some research done in the past, I don't know how to say it, but sometimes I wish that maybe PhDs were even taught a few business modules. They never had to attend business modules, because I feel like you create a great technology, but you create a great technology for the sake of creating a technology. And then, I mean, when it comes to the market, it breaks it, whether the 0 to 1 or the 1 to 10 or 10 to 100. So how do you feel like PhD education has to change? Do you feel like research has to now move towards thinking about a business problem or a societal problem first, and then research happens, or maybe research just will happen for the sake of it, and then maybe see if it happens to fit a societal problem?
That's a very good question because it really asks for the purpose of science itself or applied science and business, improving the business. So I can give you my personal opinion. Maybe in the room, everybody has its own opinion, depending where you stand. Maybe we can also discuss later on. So my personal opinion, we need some basic research just for the research, to really be free and exploring. But not everybody in research has to do this. And we need, also for the basic researchers, we need some more entrepreneurial thinking. This, I think it's key. Because in every context you can apply this. Even if you're just in the work, okay, this is basic research, then you switch off the entrepreneur in you and then do the basic research. But for all the others, this entrepreneurial thinking is super important and should be included in from the very beginning already, so that this is a kind of natural part of thinking. And then later on, it distinguishes between the pure science and then the applied science.
If I could add to it, I thought, during my PhD, there was a lot of people that were not super good at science communications, for example. And so you could see all these plots and words, but you don't really get the meaning of what's happening. And so there was a lot of push for science communications training in my institute. And over just 2 years, I saw a huge difference. So I agree that there should be more entrepreneurial workshops. But I can also say that motivations change over time. I think everyone should try to do entrepreneurship at least once in their life. So, and I think younger generations are pushing for this and inspiring, I think, all of us.
Okay, then thank you.
Okay, cool. Thank you so much.
First of all, thank you guys for joining. I appreciate the support and also for bringing in, I guess, kind of representing a big chunk of the Berlin VC community. Yeah, so I think I will let Jana take on. She will be the moderator for this session. Thank you very much.
Thank you, Isabella. Yeah, I think we start with a very short introduction of yourself. What's the best one? Let's just.
Yeah, I'm Jonas. I'm a principal with DTCF. We are a deep tech early growth fund, so like Series A is, I would say, our sweet spot. I have a background in physics, although I only have a bachelor, so I don't really consider myself a physicist compared to people with a PhD. I then worked a bit as a software engineer for Palantir, as a forward deployed engineer, which now became quite popular as a role. And I've been with now for like 4 years, and yeah, with another fund at first, and now at DTCF, and yeah, we do everything related to deep tech. So a lot of hardware, but also technical software. And in quantum computing, we invested in Kipu Quantum, which is based here in Berlin. Some of you might know, for example, Kike Solano, who's like the CEO and the founder there. And we did another investment in quantum computing in Blank QC. And it's like a neutral atom quantum computing company based in Munich, which I think you might also know, or some of you might know.
Yeah.
And which got a bit validated now with Google shifting to neutral atoms as of last week, which was like quite cool because we feel like this validates basically what Frank has been saying in the last year. Yeah.
Hi, I'm Sarah Luna. I work for the Hasso-Plattner Institute. So it's a university that was founded by SAP founder Hasso-Plattner. We have a fund called HPI Venture and an accelerator called HPI Engine, and I work at the intersection of both. I'm also a scout for First Momentum Venture, and now, as of yesterday, a scout also for a fund in London on robotics. HPI Ventures does enterprise tech that goes in the realm of SAP, so anything spanning from CRM to ERP systems. And then First Momentum is more like deep tech hardware focus. And the last one, Christian, is more on robotics. So I'm also doing a PhD right now at the University of St. Gallen on exit prediction models for startup success, adding a macroeconomical layer to make this model dynamic. It's hard, it's the beginning. Let's see where it takes me.
Cool. Hi, I'm Cindy from Luna Ventures, based in Berlin. We are a deep tech fund investing pre-seed stage company. We say the fund focus more on deep tech part, like robotic, quantum, semiconductor space. But I'm more from the bio side, do everything in biochemistry materials. I'm a biologist and computational biologist by training.
Thanks. Yeah, I'm Marcus. I'm here with LBBW. We are a fund based in Stuttgart, but I'm based in Berlin. We have the money from LBBW, which is Landesbank Baden-Württemberg, and we invested in digital transformation. What is everything? We consider everything tech in there, and we also invest in life science. And yeah, we also invested in Kipu Quantum, and for example, we also invested in Meshcapade, which was recently acquired by Epic Games. Meshcapade also a very technical founding team, spin out of Max Planck Institute. So that's also what we look very much into, to find startups with strong technology, strong technical team. And I myself also have a technical background and worked very well at Fraunhofer EC doing some research, then at Celonis, and then joined LBBW.
Okay, wonderful. Very, very tech oriented, of course, here for this audience. I would like to ask a few questions, but also give you the opportunity, because you are here for getting here the opportunity to ask the question. So I start with the question and think about what you would like to know from maybe one specific of our panel or from the group. So my first question is, what do you think is important for a great idea in a startup that come to you to get funding as we see? So what ingredients you evaluate and value for a startup?
maybe
Big start. It's very general. You pick what you would like to see. Yeah.
The cool thing is that it changes every day. So apparently we always had this idea of what do little people agree with you. So like, what is your heretical thought or your contrarian thought? And I think a good startup idea is in many cases a bit of a contrarian idea, because ideally you do it before everybody realizes it becomes like a good idea. So like if you think about, I don't know, quantum systems, they did drones in 2016 when like nobody thought about Ukraine war. And so I think ideally you then get validated 5 years later when everybody's like, oh wow, that's really something we need. But obviously that's very hard to predict. And yeah, but for me this feels like that you really need to be like one step ahead of the curve to have like a really great idea.
I think I don't think in terms of ideas. I think this is very basic VC, but you look at team, product, and market, and I usually, for example, if there's a founder with a great idea, but we don't think that the team is the right team to do that idea, or they don't have like good execution power, or we're not really sure, then maybe that idea might be, because ideas are not like they don't belong to you, so maybe you're not going to be able to do that, but a team with a better mindset and better execution power, better support might realize it better than you. So I think you can also look at, so for what you said, like you can look at the market. If, for example, you can be the first and then it has like a first mover advantage, and that's interesting, but you could also create an idea or have an idea that is in a crowded market, but maybe you're going to do it better than everyone else. And this is also an interesting thing to see. Like, what's your first mover advantage versus kind of what are the other advantages that would make you better than your competitor? It's also a good thing to have competitors. It means that it actually works and there's already people trying to solve that problem.
Yeah, I think maybe first thing first is really like what's the prioritization or mandate of a VC fund. If you're talking to an investor, you got to understand what they are looking at. What's the hard limitation, for example, geolocation or like ticket size or like, I don't know, tech. If there's a tech focus, there's a SaaS focus, or like first thing first, understand who we are talking to. I think that's actually a full question I have. And for us, we really like technical founders, scientific founders, but the problem is really always like, are they trying to solve a problem that they know, or they just have a tool and they want to find a problem to solve it? And that's a very, very hard thing. Like, right? Like, is this the best method to solve this problem, or you have a really good axe or knife and you want to cut something? So that's the problem. Also, I would echo to the contrarian part. I think good ideas and crazy ideas are usually very rewarding at the end if you look at successful cases, but I think you need to be contrarian at the good timing. Otherwise, no one will fund what the things you are doing. So, yeah.
Yeah, I feel that's like, if I can just answer on that, I feel that's a good point, because, like if you think about Webvan, it was like basically doing delivery like Uber Foods Volt, I think in 2000, and they even managed to get a lot of VC funding, but they failed spectacularly just because it was basically too early. So I guess the timing is also sometimes crucial.
I think first what I want to add is that if it's about the idea, what matters for us, what we look most into is the team and especially the execution. Because I think if we all stayed in this room for a day, we would come up with 100 or 200 startup ideas. And I think they would all be probably great ideas, but it's really tough to act on them. And that's what I realized with friends of mine who are also now in the process of founding their startups. It's like, it's not, the idea is like really not that special in most cases, but like what makes it special is the execution and the people behind it. And that's where we try to figure out very early on if the people can really make it and act on it and build a startup out of it, out of this idea or not. And I think that's also the most difficult or challenging thing to judge as a VC.
You both mentioned the team as super important. So when do you think, well, the idea is great and has potential, but the team does not fit or does not feel right? So what is then, how can you help them, or is it possible, or are you helping them with some at least advice? If they follow or not, it's on their side, but what is then your reaction Is it? Yeah.
Yeah, good answer. I think that if we're not convinced by the team, either we tell them that we're not convinced and we don't invest, or if we think they could make it, we try to give them some interest to angel investors in our network, or to other startups, or to people who worked on sort of this idea before, that they can have a chat, or that they can have a chat with them and kind of figure out if they can move or adapt and work in this field or not. But also, I don't think we're happy to help and to answer questions, but also we're not experts in this field. So if we're not convinced by the team, it's a no for us.
Mm-hmm. So team is one thing. The other one is having the solution for no problem. That's probably the other challenge. How do you handle such types of requests, I would say?
So you mean a bit like this, what Cindy said, like if you just don't have a hammer and then everything is like a nail.
Exactly.
Yeah, I mean, I feel like this is like a very difficult point, because especially like in deep tech, sometimes it is not so clear what is the perfect tool and the perfect problem. I mean, now thinking a bit, I mean, in quantum computing, there is already so many startups, so I think there's a lot of things which are quite hard now, like doing like another neutral atom startup today, or would be like probably super hard to get it off the ground. But I feel like, I think what you mentioned earlier about like quantum sensing and navigation, I think if I had like to force myself to do one idea now, I think trying to build like a GPS independent navigation for defense in Europe could be super relevant, because yeah, then GPS is still like a US solution, so might not be such a good thing for European drones and rockets and so on. But yeah, I feel like it's hard in general to judge this. Or
I think maybe more on the problem side. So first question was about idea, but we never look at ideas. I mean, I teach master students on how to build a product in a semester, and what we teach them, and we spend weeks doing that, is find the problem, not find the solution, just find the problem you want to work on for the next X years, and, you know, really define like everything that can be around that problem. And I think this is super important to nail, because if you don't have the great problem, you will never have the great solution.
I bring in questions, so I'll answer it here. So I think like every team has their own inherent knowledge and then experience before, and there's when you want to look for a question or a problem you want to work on, I think it's really about, I think this is a problem, and I'm going to validate it by talk to people in the industry and talking to people that can potentially sell to. So I think like a lot of time it's just like, I think your idea applying the space could be interesting, but can you tell me if there's really a need or if the problem actually exists? Because I personally probably don't know the field so much, right? And I need someone external to tell me this is a real problem. And I have talked to my customers, they also believe this is a problem. So I wouldn't say like it's bad to hit around, but I think it's bad when you don't know what you're hitting. Yeah.
Yeah, I mean, if there is a clear problem and you have a clear solution, it's very easy for you to raise money and everyone will understand it. If you have a solution for something where there's no problem, you have to be very good at selling it, and maybe find some investors who believe you, or maybe the investors are right, maybe you are right, as our founders right, maybe both are wrong. In the end, nobody really knows. So, but we try to figure out for us if we can find a problem, if we can get some proof on it, and if we are convinced that the startup is building a solution, and then we feel comfortable to invest. And if we don't have those proof points, or we're not convinced, then we also tell them we're not convinced that there might not be a problem, or that they're building a solution for something that is really not a big problem, and we don't invest. But also, I mean, we're also wrong very often. So it's really it's a difficult thing to say, but we try to judge it for us and then give them feedback.
And maybe even if the founders are wrong, like I think really great founders, they just manage to convince people of the problem they are believing in right now. Like, I mean, for example, when Jens Huang crashed quantum computing, then all the quantum computing stocks tanked. And I think then he said like something nice about quantum computing a year later, and then all the quantum computing stocks exploded. It was like billion of market cap shifting. But like Elon Musk is now talking about data centers in space, which I feel might be related to the upcoming SpaceX IPO. And from my feeling, it doesn't make a lot of sense right now to invest so much in that, like in space data centers. But I mean, definitely some people managed to really convince a lot of, like basically really shift the markets a little bit. And I think in quantum computing, one of the best persons probably doing this is like Nicolo, the CEO of IonQ. He's definitely like a master fundraiser, and I think he managed to put IonQ at a spot where they have, I think, $2 billion of cash. And so even if their market cap should crash, they would still be like very well financed. And they managed, for example, to buy Oxford Ionics, which from my view was actually the technological better company. And this is leading a bit better back to something what was mentioned earlier, like this fundraising issue. I mean, it's like definitely sometimes in the US you have like maybe a bit of an easier access to capital markets, but on the other hand, it's also like a fundraising game. And somebody like Nicolo, apparently he really figured out this way of like talking to public investors, and that I think stays relevant from pre-seed to post-IPO, basically. This, how do I tell an equity story? How do I convince people that I'm like the Steve Jobs of quantum computing or whatever?
You mentioned quantum computing, and we are here in the Quantum Café.
Yeah.
So this is, I think, a very interesting area, also in the VC area, to decide, is it hype, is it not hype? So how do you mentioned there must be a problem. And in the early stage of quantum computing, we have generated a lot of problems that can be solved with quantum computing, but they are far from reach at the moment. So, but nevertheless, there is potential. How do you handle such ambiguity cases where the benefit might be there and might be far in the future? How you decide then? Huh?
I can start. I think that's the hardest question in quantum or in that we have to ask ourselves when we think about quantum computing. There have to be the problems, and you also have to be right with the timing, so that it's in a time frame of the next 5 to 7 years that this solution will be relevant for the market. So that also works for us as a venture case, and we can have our exit, and we don't have a startup that's solving a problem or that's solving a problem in 20 years, because then would also not work for us. And to figure out if there is the specific quantum startups or startups working in quantum computing are on track right now and will grow into their valuation over the next 5 to 7 years or 10 years and will be great exits. Very tough to say. And we also, I mean, that could also be a question to everyone here, where there are the problems and which are the problems that will be solved within the next 5 to 7 years, and which will then be a venture case. But I think, for example, quantum is something where we strongly believing that it's solving a problem and will grow over the next 5 to 7 years. But then if it's, but it's a tough question.
I can add to this. Yeah, sure. I'll just want to hand over to the audience. Questions from the audience. I've seen one here. I don't know.
I can ask a question. Maybe just a more general question. So compared to other startup sectors like AI, do you see quantum startups, like just on specifics, you see it in any way different, or is just it's the same approach, different technology? Is there something you would say in quantum, this is what we really pay attention to? And relate to that is, do you see a trend, something that's low hanging, I don't know, like optimization, transport, quantum? Where do you see quantum in the next 5 years with high probability could have big impact? Or where do you startups like converging?
I mean, I feel this is, I can just tell it for DTCF, and there it's a bit like, everybody in the team has, I would say, different views. Most of the people in our team have like also some technical backgrounds. And then there's like 3, 4 people besides me who are also like into quantum. And I think everybody has a bit different view in the end. So I think there is really not a true answer. It's just really hard. But for me personally, I think, yeah, what you mentioned, for example, optimization, this is also something which Kipu is actually doing, because there you can show that there is applications where already today quantum computers or like computing enhanced by quantum computers is better than the baseline. I mean, the question is then on how many nodes you can like scale that. I think besides that, yeah, like what we talked or like what was mentioned earlier, this navigation, I think this is like a really interesting, or like which is something which is really ripe for application in my mind. And encryption and decryption, also because, I mean, maybe you can harvest already data right now, which you then can encrypt in like 3, 4 years. So I feel it becomes already now necessary for banks to think about, for example, encrypting their data in a way which might be immune to, I don't know, short algorithm. And I think like material science is definitely also in my mind one of the most ripe areas for application. And I think then the question is just a bit, can you also get like a big enough market out of that, or is it something which is only relevant for research, which might then still be an example of quantum computing working, but might be too small of a market size. But that's kind of my opinion.
Just borrow something that the CEO of IonQ said in the panel, which was interesting. What he said was that the world, actually, no, it wasn't. It was Dr. William Oliver next to him, sorry. So he said that the world is inherently quantum mechanical. So it's all, when we look back in time, in the future, we're going to, of course, we're using quantum for computing. And I do believe that, yeah, there's a hype, of course, but hype is like, you know, very ADHD, and right now quantum is very in. And I think it's in the development phase, and we'll look back and agree that this is the way to go. So I'm pretty confident in that myself.
Are there other questions from the audience? Oh, me. I'll go with. Can you?
Okay.
Say your name again.
I'm Pooja. So I have a question about teams, since there were a lot of discussion on the good team. Like if it is not a good team, you wouldn't invest in them. So according to like from a VC perspective, what would consist of like a good team? What is the recipe for a good team? Especially coming from a scientific background. So usually there is one scientist, of course, but then there is a tech part. But we often feel quite a lot of gap in, coming in terms with the business part. So what is a recipe for a good team?
I mean, a good team, what we look at is complementarity. So as you mentioned, there's going to be like the technical person, and usually we want like another person, which would be a business person. Most of the time, from my experience at HPI, we have only like computer scientists, and startups we work with are computer scientists or engineers. They don't really like working with business people. So what we recommend is having a team of 2 technical, like CEO, CTO, whatever you want, and then hiring like your first employee as a GTM strategist. This is something that for a go-to-market strategist, or someone that could do like all your sales process and really on one side understand what you're building, and also like go and get you VC money, clients, etc. This would be like a cool team. And then if, of course, like sweet spot, you can have like a business person and a technical person. And then there's a discussion of, is a team of 2 or a team of 3 better? Entrepreneur first, for example, they argue that a team of 2 is better. Some people say 3 is better. But yeah, I guess it's also the dynamics and how it works for you. I would say only one thing around like a good VC team, and it comes from a team I worked with recently. I think these guys, I don't know if their idea are going to be the game-changing idea of like bot protection systems, but I know that if their startup fail, they're going to start another one because it's how they do, it's in their DNA. It's just they really are very hungry, and I really see that in them. And I think this is also something that VC like to look at, and VC like to see, you know, how you know, if this fails, I will do something else because I just want to be my own boss. I just want to build something. I want to make the world better. And yeah, I think that helps.
Yeah, maybe. Yeah, I probably adding on that. So, like, let's say you go straight from like scientific world, straight out of academia, research institute, whatsoever. So I think that's probably just my way of looking at stuff. I look at how many researchers and labs is working on this topic, and I will rank if you are the top 10 or top 5 people of working on this problem. If you are the one of the best people look at this problem and know about it inside out. That's just me thinking one of the way it is a top 10. On the other hand, I'm not I know like there are people like there are technical people would like prefer to hire a business person to do all the BD or all the commercial talking for them. I do think like the very eager founder, they will figure out themselves. So I have a very good friend, he was in his PhD, starting a startup, and what I saw is really like, he knows nothing about business on day 0, but then like after a month, 2 months, he already captured so much, like even though he was the CTO, I'm like, I think you should be the CEO because you are doing all the business conversation. You are the one talking to VCs. You are the one trying to figure out you have a problem that you really can solve rather than the original CEO. So I think if you really care about problem, being a founder, like really want to capture the whole market, really want to be ambitious going through different markets, I think you will learn on the way. Yeah. And you already been through, you know, so many research and then PhD, maybe even postdocs. You're definitely smart enough to capture everything on the financial part.
There's nothing you cannot read.
Well, reading is one thing, but really internalize it that you action accordingly. So how much time would you give the founders then to also acquire this business knowledge? So just to be really on the fast track. Now, of course, everybody can learn, but sometimes it's better to take someone with this expertise instead learning yourself, which takes away the time from your core.
I mean, I feel some underestimated thing is actually job expertise. So, I mean, obviously, we always have a bit, we think of like Mark Zuckerberg and other very young founders, but there's actually economic literature that on average, founders which have more job expertise actually perform better. Because it makes sense if you're like 40 and you have like 15 years of job experience. I mean, the opportunity cost hiring yourself would cost more than hiring yourself like when you're right out of college. So to some extent, you just have probably more impact also on the business side. And I agree with Cindy that if you do something very technically, I mean, it's best that you are really good in what you're doing. And I mean, my sanity check is always I just type people into Google Scholar. And if, like, for example, when I typed Kike from Kipo in Google Scholar, he has like an age index of 100 or something, he has 20,000 citations. That needs 1 minute, and you're like, okay, this guy is serious. He has like done leading work in his field. And I also feel like, yeah, you should probably try to get co-founders, because if you cannot find a co-founder, then it will be also hard to find like partnerships, VCs, and so on. But yeah, I feel it's like with this question, can people work themselves into new kind of roles? I would say, yeah, definitely. And I would also feel like that you should give the founders then the time to figure things out. We are talking right now with a startup where there's kind of 2 technical founders, and one of them, he's kind of a genius. And so now he also happens to be the CEO, which is to some extent good, is to some extent also not good, because like he should maybe spend more time on research. So I feel like sometimes there's also just not the perfect answer to that.
Seen some more questions from the audience?
I would actually want to comment on this question that's, sorry, actually, and yours. Yes, so I'm not a VC, but based on my experience with VCs, the ideal team is essentially a scientist with a brand institution or lab, because honestly, VCs have no idea which lab is best. They know which lab is considered best. So they cannot tell. So what you want to have is, some labels of, institutions, top companies and so on. And from the science perspective, and then the co-founder who can oversell. Who can essentially, tell the guys what he wants to hear, what's, picture the, picture the way that kind of blends with the VC perception, and then you have, a very good to go to.
Yeah. One question? You have one question? Yeah, I have a question. So, I mean, you're also working in teams, right? So how's your process of evaluating whether a business idea is worth pursuing or not? Like, how do you interact within your team? And also, if you don't feel like you have enough knowledge to really understand the business idea in the depth that you need to, how do you get it? Like, what's the process in your teams, in your individual teams?
I mean, so we basically, we always, you basically, in order to get an investment from us, you need to convince one person of the team first. And then this person basically needs to convince the other people in the team, maybe not to the same extent, but enough so that everybody says, okay, it seems fine. And this can be a very long process. But so basically, one person first and then the majority of the team next. And this is something which this person has to figure. And I think from this outside perspective, sometimes helps you if you're talking with a VC fund for 3 months and you feel you're getting nowhere, then maybe try to ask a bit like, hey, what do your colleagues think? I think how we do it is like we do also a lot of references. So when we invested in Kipo, for example, I also called Jens Eisert, who is a professor here in Berlin, and it was very hard to get like 30 minutes with him. But I think if you're persistent, then you can get like ref calls from people from your network. And we also sometimes just pay for ref calls. So there's platforms where you can like pay $700 to pay with a certain person in a certain field. So I feel like VCs, even if it's maybe sometimes true that they don't really have a clue about the field, they're usually good in getting people who know stuff and then ask them. And I think this is like probably how VCs work. And then it depends a bit how technical they themselves are. Like in our team, since we have several physicists, then we also really like dig into papers sometimes and discuss that. But I guess this really depends on the fund. But Luna, I mean, you're also super technical, right? So I feel it's also
maybe from our side, our background is like mixture of computer scientists. I'm more from bio side, and there is like chemical engineering. So we try to have even venture partner for a specific topic we look at. For example, if we look at materials, then we actually have a proper venture partners in place that we asking every questions we have around idea or around material science. We say so first, like papers, like checking if if it's come straight out of research, then checking papers definitely works. Knowing what's the forefront of the field, what they're working on, where they are going, actually match with the field. We also do. I personally also do references, but depends on what kind of problem you are solving or what kind of customer you want to go for. Then I will ask my friend in pharma or in biotech. So that's the way I do it. Regarding process, I think you do need to persuade that person, the first person that you talk to in the fund, or on the other way, saying like you need to be very careful at picking the first person you talk to in the fund, because in our fund, everyone has a different focus. So if you ask me something about semiconductor, I will tell you, hi, there is my colleague. He is working on that topic. Please talk to them. Then talking to me, because I will not add any value to support your idea inside of our team, because I know very barely anything about semiconductor, right? So I think picking the right person in the team to talk to as the first person would be very important. And then for us, we are very small, so we just like one person look at the idea and then bring it into the team. One person look at the idea, maybe have the deck, and then have a first call, and then bring it back to the team. We have a very quick discussion about things, and then we see where do we go from it. Yeah.
Yeah, I'm wondering about how you think about timing, because I think you mentioned that So kind of like looking for some sort of liquidation event 5 to 10 years after investment, right? Thinking about typical fund cycles. Now I think in deep tech, that sounds sometimes ambitious, right? Like thinking about super long research times, and I imagine it's also probably challenging to really understand sometimes where in this technology readiness journey the company really is. I don't know, I think about companies such as BioNTech. I think they were founded in 2008 or something. Then COVID hit, I don't know, 13 years later. So how do you think about this sweet spot for you as VC when it makes sense to get onto that journey? Also the other way around, maybe for founders thinking about raising, when do you think, okay, it's better maybe to first go through public funding, government funding? How do you think about this, the aspect of timing?
That's a good question. I think what separate from deep tech is, I think, by itself. So also, but it also has to be like more or less fit into this typical VC life cycle. But that's also a reason why it makes it so hard for some deep tech startups to raise, or why they have to go to specific deep tech funds. That's the last question to you then. But if it's a technology that will only be ready for like this liquidation event in 20 years, it will be a tough VC case, because the IRR, and as soon as you get into VC, your startup essentially becomes a financial product, and this financial product is measured by how much return it generates for the investors. And investors want to have at least like 2 double-digit growth over each year, so that you have like this at least like or somewhere in the 10x range of this liquidation event, so you have generated returns. And that doesn't work for some deep tech startups, and it also doesn't work for, well, in my opinion, it will be also very tough for some defense tech companies to generate this return in like this time frame. But maybe it's a bit different. Focus or started from life science, for example. That's something where we also invest in, and that's what the reason why we have an evergreen fund structure, because in life science it's exactly the case that some investments, for example, biotech, that they don't fit into this 10-year range. So that's why it works for us, because we think, okay, if it's a great event or big liquidity, and then in 12, 13, or 15 years, it could still make sense for us to invest, and we have a bit bigger focus. We are not that stressed about our liquidity, because we have money from the bank, so we can invest and we can make it work if it takes 15 years. And I think also many other funds are now considering this, especially now with IPOs are getting postponed. So it's very difficult to, even for this typical SaaS business fit into this time frame. I think this is getting a bit more relaxed. And for the startup, you have to decide where you fit. If it's like 5 to 7 years, maybe it's 10 years, maybe it's even longer. And then also address the appropriate funds. If there's some funds for them, it works. There's public money and it works. Maybe it doesn't work at all. And then it's also clear that it's not a venture case, and you have to find some other source where you can get your money from. Yeah.
Maybe to build a bit on that. So there is actually studies also on the performance of SaaS VCs versus deep tech VCs. And interestingly, I think median is kind of similar. The advantage you have with a deep tech VC is that you have more time to do your due diligence. Like in SaaS, there is like a lot of hype rounds where basically even the Quantums of this world or Sequoias have like some days to decide. And in deep tech, it's usually like you to do your thorough due diligence. I think in biotech, it's even longer. I feel like in biotech, like people can really take like months to decide, even if this is like one of the super competitive cases. So I think this is a bit of an answer that deep tech VCs still seem to work, at least in the past. You never really know about the future, and right now the funding environment is definitely way harder than it used to be. And the way I see this is that it's really hard to get like a lead investor to invest in you. Let's say you want to do your pre-seed round. If you get a fund like Luna Ventures to say, hey, we want to lead this round, we want to do like, I don't know, 1 million, then it can happen quite fast. And then a lot of people are jumping in and saying, hey, we would also like to become part of this round. And then the rounds actually, it feels like that the rounds are getting larger, and at the same time, it's getting harder to actually raise rounds, because I feel there's a lot of insecurity, and then people like to go into rounds where there is already like a lead investor. You also mentioned public funding. I mean, the fund I work for is publicly backed. We are backed by the German government, so to some extent we are a public fund. I feel that on average, venture capital is helping you more than like exist or something. I mean, it doesn't mean you cannot go for exist, but I mean, if you get money from a VC fund, you can just start ripping. If you get exist, then you have like more red tape. So if it's like either or, I would always go for venture capital. But especially like in quantum computing, and this is I think something you mentioned earlier, it's so important what the government is doing. And I think we could talk like a whole day only about what would be the best way for the high-tech agenda. And it's certainly not perfect what Germany is doing, especially compared to what the US or China are doing. But still, like, I mean, you also like, yeah, I mean, my short answer on that is I think the German government should push more money into companies like Planck and IQM, which are on their way to IPO. And in the past, the Steel Air initiative was very like defocused, and it kickstarted a lot of very small startups, which a lot of them are now struggling to do actually Series A. But this is like another discussion.
More question.
So Sarah and Marcus, you mentioned two things that you evaluate in the pre-seed round is how's team and if they're capable of executing it or not. So team part we already discussed. I'm curious to hear about how do you evaluate if they're capable of executing the idea or not?
Yeah, I mean, usually, I mean, it depends on how early they are, right? Like, sometimes what we do is that since we have an incubator and then we could invest at the end, and we also have a fund where we just source startups and then invest in them, I guess the behavior is different. In the incubator, I'm going to look at each team, how they perform. We have like a demo day at the end, and you can actually, and sometimes it's not even about like how strong they are at building and going all in on their problem solving. It's also maybe taking the lead of pivoting, like you test, and I think the big word we love is iteration, but it's so true, right? So you just try and fail. Also, one thing you mentioned that was very true is, do you do enough like customer validation? Do you try to call enough people, talk to your customers or potential customers? Like, are you very like active in a way of making this thing work? And do you have like a clear roadmap of how you want to do that? This is something we really like to see, that you have like a roadmap in head of, hey, I want to be there and I'm going to take all these different steps to make it work. You know, I don't know if you have.
Yeah, I don't have anything.
Cool.
Okay, unfortunately, we are already at the end of our session, so it was kind of quite fast. We talked about a lot of visuals you would have as we see for a good decision. Yeah? Good team was one thing, really solving a problem, coming structured, having a kind of plan on how to. So maybe everybody a final remark to close this, maybe a wish you have to founders that come to you, or an advice, a recommendation. What would you like to tell them?
Do you want to start?
I have to think.
Okay, I can tell you, I mean, it's super easy, and it was said already, but make sure that you target the right people. Make sure you know who you're talking to, what they invest in. I receive a lot of like inbound flow on LinkedIn, but most of the people don't really look at what I'm doing, what I invest in, or like it's in the easy information, saves you a lot of trouble, saves me also the trouble of saying you know. So I think, yeah, just make sure that you target the right people you're talking to, because you also have then more chance to have a call with them. Yeah.
From my side, maybe one very important problem is, do you want to be a VC backup startup or are you not? Because as we discussed, timeline is ultra important. You need to be able to raise the pre-seed now, and you need to be able to raise the seed in a year, how to reach there, what's the people expectation metrics, and then you need to be having a big enough liquidation event by the end of 7 to 10 years. Do you think what you're building will make that happen? So that's my, one tip around this.
I'll go ahead.
Mato would be more still more technical spin-offs from university because there's a lot of great foundational research happening in Germany, and there are not so many spin-outs. And usually, what we got most of was investing in those spin-outs. So we're looking for more, and from like this Max Planck, this Fraunhofer, this Hasselblad, there's so many research facilities, and there's so many great researchers at those facilities. And yeah, I think there's a lot of potential for many more startups in Germany, and that they can be founded in Germany and not just go to the US and then be founded in the US.
Incorporating that aware.
Yeah, maybe like if you think if you should do it, probably just do it, because I think in Germany there's like, I would say, a gap of entrepreneurship. So I think if you decide for doing your own startup versus, for example, joining a startup, there is like a high likelihood that this also is for you the better outcome, even if you don't manage to do an IPO. But like I think founding a startup can really lead to a lot of career growth.
Okay, great, wonderful. So thank you for also to you for coming here.
One big just picture from everybody, and then that's it. Thank you.
Where?
I'll take it from here.